Hi everybody, welcome to round 1 of 2019. Just before we get started, I want to mention a couple of changes. I've obviously changed my IDE to VS Code because it's a lot more pleasant looking and it has a dark theme which is easy on the eyes, although I still need to change this PDF reader. And I've also added dependencies commented out above each answer in case that this capture all header file doesn't work for you. So other than that, let's get started. So in this first question, we're given 3 space-separated integers, and we're asked to first determine if it forms a triangle, as in if all the angles add up to 180. And then, if it does, then we're asked to determine what type of triangle it is. So the only thing that is important is the order in which we check each expression, let's say. So first we check that all 3 angles add up to 180, and if not, then we output impossible. And then otherwise, if all the angles are equal, we output equilateral, and if not, then we check if 2 angles are equal, in which case we output isosceles, and if none of those are true, we output scalene. So if not all 3 angles are equal, then if we check that 2 angles are equal, it's impossible that all 3 will be equal. So we don't need to check that, for example, just with using this first expression, we don't need to check that A is also not equal to C, because we've already checked this up here, if that makes sense. And that's it for this question. It's quite simple. It's a couple of test cases. The input goes down here, if you can see in the bottom left corner. Output's isosceles as we expected, and let's try one more. We'll try 50, 60, 70. So it just needs a bit of time. Scalene. And then finally, we'll try one impossible case. And then just the equilateral. Yeah, so it works just fine. Okay, so for this next problem, we're given an integer n, and we're asked to output the nth prime. So that's simple enough, but the only problem is your solution has to have the time complexity of big O of log n, or n log n rather, and because we have such a large test case, and there's no ways you can do this using a quadratic solution. So let's just go through how we're going to do this. So before I get into the actual solution, let's say I'm just going to run through this function that I've created above here of Boolean type, and it's going to just determine if a number is prime or not. So it takes in a number as a constant and as reference. The reason we take it in as constant is so that it's just good practice if we're not going to make any adjustments to the number within the function, and then as reference so that we don't create a duplicate of the number. It just saves memory. It's good practice. So let's run through this line by line. So the first check is whether the number is less than 2. If it's less than 2, then of course it's not prime. Then this next line, if it's equal to 2 or 3, it is prime. And the next one, this is an interesting way of eliminating even numbers and numbers divisible by 3. So if the number mod 6 is not, note this exclamation mark, so if both of these evaluate to false, then this entire statement is true, in which case it returns false. Sorry, it's a bit confusing to wrap your head around, but just to take a moment to read it. So the reason this works is because if a number mod 6 returns 0, 2, or 4, then it's even. Otherwise, if it returns 0, 3, then it's divisible by 3. So all prime numbers mod 6 are equal to 1 or 5, but not necessarily all numbers mod 6 equal to 1 or 5 are prime. So that's just one thing to note. It's just a quick way to eliminate a bunch of possible numbers. Then this final line is quite important. This allows us to determine the primality of a number in O of log n time. So we're going to run through from 5 to the square root of the number. And we are going to check if the number is divisible by I, in which case, if it is, it returns false, because then it has one more factor other than 1 and itself, or itself, yeah. And at the end of this, if all of these don't go through, then we return true. So these first 3 statements will eliminate all even numbers and numbers divisible by 3, and but then 5, 7. Let me just think, 11, 13, 17, 19, and 23 will pass through. And then 25 will be the first number that passes through this thing, because remember, I has to be less than or equal to the square root of the number in order to execute this for loop. So, so 25 will be the first one to go through, and the square root of 25 is 5. So since it is divisible by 5, it will return false, as in it's not prime. And the reason this line works, or the reason why running to the square root of the number works is, well, I'll show you here in the paint document. Well, the factors of a number exist in pairs. I'm using 50 as an example. You can see that the pairs of factors are 1 and 50, 2, 25, and 5 and 10. Then they just invert and repeat. So all you have to do is run to the square root of the number, either or lesser than or equal to the square root of the number, in which case, oh sorry, it's not 5, my bad, it's actually, I'm thinking of 25 now, it's actually a 7 point something. So it will run to, you know, the largest number less than or equal to the square root is 5, so it'll run to about 5. And if it's divisible by that number, then it's not prime, if that somewhat makes sense. It's just an interesting property of the factors of numbers, that there's a smaller number and its pairs of factors is always less than or equal to the square root of the number. So that allows us to check the primality of a number without running to the number itself. So yeah, that's that. Now in the actual solution, we're going to input integer n from the input stream, and then we are going to declare integer I equals 2. This is the number that's going to run to well, we're just going to carry on incrementing and checking if it's prime. And then the counter is going to record the number of primes that we've found so far. So of course it's initially 0. And then we enter into this while loop as long as the counter is less than n. So if the number I is prime, then we increase the counter. We've essentially found a new prime number. Then we increase I. So initially, when we come into this loop, I will be equal to 2. And of course, 2 is prime, so we increase the counter, which means we found our first prime number. Then I becomes 3. It goes back in so long as n is larger than 2, or 1, rather. And then checks that 3 is prime, which it is, so increases the counter, and so on and so forth. And eventually what happens is we find the final prime number, and then we increase I one more time unnecessarily. So for our output, we output I minus 1. So that's just important to note. That's the end of the solution. On to question 2.2, which is an extension of 2.1. So in this question, we recycled the primality tester Boolean function. So just make sure you don't lose it from the previous question. And you'll see why we're going to need this in a moment. So now onto the actual solution, we're going to input integer n from the input stream. Then we're going to declare this data structure that you may have not encountered before, which is called a queue. And we're going to push the 4 single-digit prime numbers into it. And you'll see why I'll do this in a moment. And we're going to initialize counter to 0. So I'm going to show you how this queue works. Over here, we can see that you know, we push those 4 single-digit primes in, and this is the order in which the elements appear. So the frontmost element is the first element that was pushed into the queue, just like queues work in real life. So the items that are pushed onto it are entered into the rear, so that would be back here, and then they gradually get to the front of the queue, and the first thing that enters the queue is the first thing to exit. So to return the value of the frontmost element of the queue, we use the function q.front, and a q.pop removes the frontmost element from the queue, so that would be 2 in this case, if we want to pop it. The only way to access these numbers behind 2, let's just say that 2 was still there, the only way to access 3, 5, and 7 would be to pop 2, so you would have to continuously pop these frontmost elements and then return q.front. So let's just say we pop 3 and 2, we use q.front to return 5. So that's the data structure we're using for the solution. So now what happens is we enter into this loop while the queue is not empty. This returns a Boolean value, so if the queue is empty, it returns true. But as long as it's false, you know, you can see this exclamation mark here, it enters into the loop, and the counter pre-incremented is not equal to the nth truncatable, right truncatable prime. Or sorry, no, just the value of n. So this pre-increment is quite important. If we place this after, what it would do is it would evaluate the equivalency of counter to n, or non-equivalency rather, and then increment counter. But if we pre-increment, what happens is we add 1 to the counter, and then we check for non-equivalency to n. So I'm going to just jump into a paint document to show you what exactly is happening in this loop, because it's a bit difficult to understand. So let's just say that n is equal to 1, and of course our counter is initialized to 0, as you can see over here. So we first go to the statement here to determine whether we'll enter into the while loop or not. And so the queue is not empty, of course, since we push these 4 elements. And the counter pre-incremented, so let's just increment counter. It's now equal to 1, and then we check for non-equivalency. But since n and counter are equal to each other, we won't even enter into this loop. So what that gives us, what happens is we pass over this while loop, And then we check that the queue is not empty, which it isn't, and so we return the frontmost element, which is 2, the first item that was pushed inside. So now let's just say that we do enter into the while loop. So what happens is we pre-increment the counter, check for non-equivalency, and they aren't equivalent, so we will enter into the front of the loop. So now what happens is we check, store queue.front, the frontmost element of the queue in P, which would be 2 in this case, and then we pop that element from the queue. So we're going to pop 2 off, and now P is going to be equal to 2. And now we're going to iterate from 1 to 9, all the odd numbers from 1 to 9. And this is interesting, so we're going to multiply P by 10, and then add all the odd, or essentially append all the odd numbers to 2. So by multiplying by 10, we're adding an additional digit to P, and I is just going to essentially place odd numbers in that second placeholder. So it'll look something like this. So that multiplying by 10, like I said, adds a placeholder in the units and essentially shifts the numbers to the left. And now we're just going to add all the odd numbers from 1 to 9 here, and then check if that number is prime. So you can see if it's prime, then we add it to the back of the queue. So 21. Sorry, my writing's a bit bad. Well, this one isn't prime, so we're going to discard it. Try 23. It is prime, so we're going to add this to the back of the queue. Then 25, not prime, so we're going to discard it. 27, not prime, and then 29. It is prime, so we add it to the back of the queue. And then we finish with that for loop. So now we go back to the beginning of the while loop. We pre-increment the counter. Now the counter becomes 2. And we test for non-equivalency. They aren't equivalent, so we enter in. So now P equals the frontmost element, which in this case is going to be equal to 3. And we pop that element, so we remove 3. For I, okay, now we're going to do the exact same thing we did with 2. So we're going to put 3 here, and then in this placeholder, we're essentially adding a placeholder in the units. And we're going to put all the odd numbers there. So we check 31, which it is prime. So we're going to add this. Sorry. And then we're going to try 33. It isn't prime. 35, not prime, because it's divisible by 5. 37, which is prime, so we're going to append that. And then finally 39, which isn't, because it's divisible by 3. So now we finish with this for loop. And then we come back to the beginning of the queue, and we pre-increment the counter, and now the counter is going to be equal to 3. And we test for non-equivalency, which they are equivalent, so we're not going to enter into the while loop. So now we're going to go back here. We check that the queue is not empty, which it isn't. We can see these are all the elements in the queue now, excluding 3 and 2. And we're going to return the frontmost element of the queue, which is going to be 5. So you can see the number of elements we pop is n minus 2. So essentially, the right truncatable prime we're looking for is n positions to the left, if that makes sense. So this is the 3 positions to the left, and if we're looking for the first right truncatable prime, well, it's going to be 1 position to the left. And so what we're doing is we're constantly appending right truncatable primes to this list, to this queue, and then popping off the frontmost element until we get to the nth position from the right. And so hopefully that makes sense. I'm not going to do another example because this takes quite a bit of time, but I think it should make sense as I've explained it. So that's it for this answer. Let's let me also just test a couple of test cases, because we do have some pretty large ones. Oh, and I also should mention the largest right truncatable prime is 739399133, which is the 83rd right truncatable prime, and that's quite a small test case considering that we're doing this in O of n log n time. Or actually, maybe even less. But anyways, that we can do that very quickly, so we don't have to worry about excessively large test cases. So I'll try some of the smaller ones. Let's say 5, we get 23. Then if we try, let's just skip right to the largest test case that they've given, 50. And then finally, I'm going to try 83, which is the largest right truncatable prime. You can see we get this number over here. And the reason for that is because if we append odd numbers here, all of the numbers with odd numbers appended to it, so let's say it would be this, or this, or this, or this, or this, All of those are composites, so this is the largest right truncatable prime. So for this next problem, we're given a string of all capital letters, and we're asked to find the lowest occurring digit word, if there is one, in the given input, and the order of characters in which the digit word occurs inside of the input string has to be the same as the order in which it occurs in the actual digit word. So what I mean by that is, well, let's just use bounce as an example. O, N, and E occur in the same order they do in 1, if that makes sense. If there's no digit word within that word, then you just return none. Hopefully that's simple enough. So now let's see how we implement this. So we first create a list of digit words, and of course it's going to have length 9, and we put order the elements in ascending order, and you'll see why in a moment. And then we're going to declare input string and then input it, and now we're going to enter into this pretty big section here, which is a bunch of for loops. And the idea is we're going to run through each digit word within digit words, and then each character within that digit word, and then check for equivalency of that character to each position in the input string. And if it finds all the characters of the digit word, it outputs that digit word and then breaks out of the program. And otherwise, and this return 0, just breaks the program. And otherwise, if it finds nothing, then it outputs none. So I'll show you how we do this in a Paint document now. So I'm using bounce as an example here. So what we're going to do is we're going to run through each digit word in digit words. And since, like I said, the list was made in ascending order of digit words, the first one that we go through, or it's going to go from 1 to 9. So what happens is if we'll essentially output the lowest occurring digit word, if that makes sense. So now we're going to initialize characters found to 0 and the last index to -1, and you'll see why we do that in a moment. And now we're going to run through each character and digit word, and we're going to have I equal the last index plus 1. So the reason we initialize it to -1 is so that when we add 1, it will become 0, which is the first position of the input string. And then we're going to have it run to the final character, or the final index in the input string. So it's length -1, because the length is actually 6, and -1 gives us the index of the final character. And then we check if the input string at that particular index is equal to the character, in which case if it is, then we set last index's value to I, which is the position in which the character was found, and then we increase the characters found. So in this way, let's say we find O, what happens is we set the last index to 1, and then when we come back into this for loop, we go to the next character, which is N, and now we run I from the last index plus 1. So now we're checking from U to E, if that makes sense. So that's how it's going to work. And in this way, we make sure that, for example, we don't by mistake count N as valid if it occurs before O, if that makes sense. Okay, so now let's run through this line by line. So we're going to have, like I said, these values initialized to these, and then we're going to run through each character and digit word. So we'll start with O in 1, and for I equals last index plus 1, so this becomes, oh sorry, actually it remains -1, but I will be equal to 0 now, to the input string of length -1. So if input string at index 0 is equal to C, well, we're checking for equivalency and they're not, so we're going to run back to the beginning, and now I is going to be, we're going to add 1 to I, so now we're checking O. O is equal to the character, so we're going to change last index's value to I, which at the moment is 1, and we're going to increase the number of characters found by 1. And then we're going to, oh, that's bad. Then we're going to break out of this loop, and we're going to go to the next character and digit word, which is N. And now we set I equals the last index plus 1. So now we're going to check from U to the end of the string. And if input string at this index, which is 2, is equal to C, well, it's not. So we're going to go into the next character, increment I by 1. And we're checking N's equivalency to the C, the current character we're looking for. And of course this is true. So we change last index's value to 3. And then we add the number of characters found by 1. So we get 2, and now we go to the final character, which is E. Then we go back to the beginning. The last index, I is now equal to the last index plus 1, which is 4. So we're checking from C to E. So C isn't equal to E, so we're going to go to the next, we're going to increase I by 1 and go to the next character. E is equal to E, as in this character in the input string is equal to E, the current character that we're looking for. So he's finally set last index to 5. This part's not really necessary, but we're going to do it anyways. And we're going to increase the number of characters found by 1. And we're going to break out of this now, and we have no more characters to go through in digit words because we've exhausted the number of characters. And now we're going to check if the number of characters found is equal to the digit words length. So the length of digit words is 3, you can see the 3 characters, and the number of characters found is 3, so we print the digit word, and return 0 just breaks out of the entire program. So in the case that we don't find the digit word, then what happens is we go to the next one, which would be 2. And if we don't find 2, we go to 3, up until we reach 9. And if nothing is found, then we won't print any digit word, and we're just going to output none. So I think that somewhat made sense. Now let's test a couple of examples. So we'll start with bounce, which should give us 1. That's right. So in code, will give us none. Ooh, sorry, I made a mistake, yeah. We get none, and then Sphinx should give us 6. Sorry, I have to give this program a bit of time before I input anything, because it's compiling, I guess. Founder should give 1. And now these ones, I have to actually copy this into my IDE, and then put it on one line, otherwise it doesn't work in the terminal. So let's run this. And this one I believe gives 8. Let's test. Yeah, okay, that's right. And yeah, that's about it. So this is a fully functioning program. So anyways, that's it for all the questions. I hope that was somewhat helpful. I'm hoping to have 2018's round 1 up sometime soon. I'll see though, since school's getting started. Also, I'll see how much time I have in my hands. Anyways, cheers.